Hi, everyone. I'm going to record a video about some of the problems on homework 4. In particular, problem 2 asks you to do some unusual stuff with intersections and unions of intervals in the real line. And we haven't seen a whole lot of that, so I'm just going to do one quick example of first how you would even think about a problem like this, maybe come up with a guess for what a simplified version of, say, this union of intervals would look like, and then how you'd actually prove that your answer is correct. So um, this isn't exactly one of the problems from the homework, but it's kind of similar. So hopefully it gives you an idea of how to approach the actual problems. And hopefully this doesn't take too long. So let's say we want to write this union of the closed intervals from 1 over n to 1 minus 1 over n. With as few steps as possible. Okay, I claim I can do it in one. You might not always be able to, but I claim for this one we can. Okay, so the first thing we're going to want to do here is we're probably going to want to assign names to these things, just so I don't have to keep writing these big intervals down over and over. So we're going to call the interval from 1 over n to 1 minus 1 over n just a sub n. And then this whole thing we're just going to call a. So a is the union of all the an's. Note, n is going from 3 to infinity. I just chose 3 arbitrarily. We should get the same answer no matter what starting index we pick. Unless it's some absurd starting index that doesn't make sense. Anyway, all right, so the first thing we're going to want to do here, number one, I'm going to say start by drawing a picture. Okay, drawing a picture isn't going to help you prove it. Well, it might help you prove it. It's not going to be a proof in its own right, but it'll help us start thinking. So I'm going to draw a little number line, 0 to 1. I'm drawing it from 0 to 1 because no matter what integer n I pick, greater than or equal to 3 at least, these intervals will be contained in the interval from 0 to 1. So for example, let's write some out. A3 would be the interval from 1/3 to 2/3. A4 would be the interval from 1/4 to 3/4. A5 goes from 1/5 to 4/5, so on and so forth. And so, okay, that first interval, let's look like that. So that was A3. And then there was 1/4 to 3/4. That was A4. And then it's getting bigger, we can see, right? That's A5. And then you'd keep going, right? You'd get a bunch of these. And you might wonder, okay, does it always stay contained in 0, 1, or does it go past it? And for that, I can make maybe a little calculus argument. Using limits. And again, this won't exactly be a proof either, but it'll get you started. So I could think, okay, what's the limit of the left endpoint of this interval? Right, as n gets bigger, so as I'm taking bigger and bigger unions, what does 1 over n approach? Approach to 0. So you should expect that eventually, we'd get super, super close to 0 here. Similarly, as I'm taking bigger and bigger unions, the limit of this right endpoint, 1 minus 1 over n, should just get closer to 1. So again, you may never hit 1, but you'll get really, really close. So that's limiting behavior. Okay, and then step 3 is make a guess, which maybe sounds not very mathematical. but there are only 4 possibilities at this point. We know it's an interval from 0 to 1. It's either going to be open on both sides, closed on both sides, or open on one, closed on the other. There are only 4 options. And racking your brain a little bit, you could probably guess which one is going to be correct. Okay, so as I was saying, we're limiting here and we're like approaching from the inside, right? We're getting closer and closer to 0, 1, and it's like percolating outwards. But we're never going to hit 0 and 1, right? I mean, I guess the limit is literally equal to 0 on the left, and the limit's literally equal to 1 on the right. But if I take any of those sets right here, if I take any of my ANs, no matter how large n is, 0 is not going to be contained in it, 1's not going to be contained in it. Okay, so using that, I'm going to say this is my guess. My guess is it's the interval, the open interval from 0 to 1. Okay, the last step is going to be prove it. Okay, so here's my claim. My claim is that my set A, remember, I'm just calling the union of everything capital A. So my claim is that capital A is the open interval from 0 to 1. And that would definitely be the smallest number of sets I can use to describe it, right? We started with infinitely many here, and I was able to reduce to just one, supposed to be. So let's prove this thing. And maybe I'll keep a reminder here what A is, so I don't have to keep scrolling back up. A is that union. All right, so that's my claim. And in order to prove that, you can remember that equality of sets, these are both sets, 2 sets being equal means one is a subset of the other and vice versa. So let's prove it both ways. Let's prove A is a subset of 0, 1 first. So WTS means want to show. I want to show A is a subset of 0, 1. Okay, so let X be an element of A. Then I want to show X is also an element of the interval from 0 to 1. But what does it mean for X to be an element of A? Well, it means X is in this union. Then if I'm in a union, I have to be in at least one of the sets composing that union. Be in at least one of these intervals. Maybe more than one, but definitely at least one. So I could say for one of these intervals, let's call it the nth interval, because why not? So n is some natural number. So I'm saying there exists a natural number n, sort of an index of our A sub n set, such that X is in A sub n. Instead of A sub n, maybe I'll just write it out. X is in this interval from 1 over n to 1 minus 1 over n. Okay, hopefully that's clear, right? This is just one of the A sub n's. So it's just the definition of what it means to be a union of sets. It means to be an element of a union. Okay. But what does that imply? Well, that implies that, let's just write out what this means. If I'm in the closed interval from 1 over n to 1 minus 1 over n, that means X is between those two things, right? Means X is greater than or equal to the left endpoint, less than or equal to the right endpoint. You guys will see this come up if you ever take analysis, real analysis. Okay, so that's what that means. But how does that help me? Well, I want to get here And for x to be in the open interval from 0 to 1, it better be strictly greater than 0 and strictly less than 1. But note, we can note two things, two little bullet points. This left endpoint here is always positive, right? No matter what natural number n I pick, 1 over n is positive because the natural numbers themselves are positive. So I could say no, 1 over n is strictly larger than 0, no matter what I pick for n. All natural numbers, that's true. Similarly, I could say 1 minus 1 over n. Well, that's 1 minus a positive number, so it's definitely less than 1. Again, strictly less than 1, no matter what I pick for n. So with that, I have some interesting facts. Interesting facts are, okay, 1 over n is greater than 0, but also 1 over n is less than or equal to x. So let's string those things together into one giant inequality. I'm going to turn this around. I'm going to flip it and say 0 is less than 1 over n. And then 1 over n is less than or equal to x. Similarly, x is less than or equal to 1 minus 1 over n. So let's write that down. And 1 minus 1 over n is less than 1. Okay. What does that mean? Well, if we just focus on this, just do this. We just focus on that part of the inequality that's saying 0 strictly less than x, strictly less than 1, which means x is in the open interval from 0. Open because we're doing strictly less than here. It would be closed if it was less than or equal to. Okay, and that's what we wanted, right? We started with some element in A, showed it had to be in the open interval from 0 to 1. Therefore, A is a subset of the open interval from 0 to 1. But that's only one direction. If we want to show equality, we have to go the other way as well. So let's do that. Drop this direction and say, so 0, 1 is a subset of A. Okay. So looking at the whole proof, here's what we have so far. We showed one directional containment. Now we're going to show the other. All right, same story. Let x now be an element of 0, 1, open on both sides. This one's going to be a little trickier. Okay, so what does that mean? Well, that means, as we said a second ago, we have that strict inequality. And I could actually break this up into two. Say 0 is less than x, and x is less than 1. That inequality means, right? So I could write it like that. Okay. I'm going to need to make use of something here that I don't think we've covered in lecture. So this might be overkill, but this was good to know. It's usually taught in a Math 8 course, and I think it's in your textbook. So it is something you should know. So listen up. It's called the Archimedean property. So by the Archimedean property, and I'll basically tell you what the Archimedean property is here. The fact that 0 is less than x means, okay, if I put these on a number line, 0 is here, x is here. Maybe x is super duper close, right? Maybe x is like 0.00000054 or something. Maybe it's super close. But the Archimedean property tells us that no matter how close two real numbers are, I can always find some particularly nice number here, call it 1 over n, that's between them. Okay. So by the Archimedean property, there exists, maybe I'll stop using n, maybe I'll use k. There exists some integer. Yeah, in this case, I can say natural number, why not, since everything's positive here. There exists some natural number k, such that 1 over k, maybe I'll do this all together. 0 is less than 1 over k, which is strictly less than x. Okay. That's true for all positive numbers. Okay. We've seen something similar. We've seen that if I pick two positive numbers, I can find some positive number between them by taking their average. This is actually slightly stronger than that because this is saying it's like 1 over some natural number. Whereas like the average here, you might not be able to represent as 1 over something. In this case, you can, right? So we have that, and maybe that's not surprising, right? Like if I pick this number x, then maybe 1 over k is 1 over, I don't know, let's just be excessive and say 1 over a gigantic number, right? So it works no matter how small x is. Okay. And similarly, I could say there exists some, maybe I'll pick a different letter, m, again, natural, such that, well, let's figure out this one. Okay, so I might have to rewrite this. Okay, so let's rewrite this as, what do I want to do? Let's say 1 minus x is positive. I'm just subtracting x from both sides. Didn't fundamentally change anything about that inequality, but that'll be nice to work with. Okay, similarly, since 1 minus x is positive, there exists, by the Archimedean property, some natural number such that the following holds. Let's see, how should I write this? Yeah, this is fine. 1 over m is less than 1 minus x. The same story, right? Up here, x was some positive number, so I could find some 1 over a natural number less than it. Now 1 minus x is a positive number, so I can find some 1 over m less than it. The annoying thing here is m and k might be different. So let's erase this. But what I can do, okay, maybe I'll draw a picture. Let's put 0 and 1 on here. And let's say I picked, I don't know, x equals 0.24 or something. The Archimedean property, these two facts say, okay, maybe I'll pick k equals 10. So this is the number 1 over 10. 1 over k equals 1 over 10. Right, definitely less than x and greater than 0. But for m, I had a lot more leeway. Maybe I was silly and I picked like 1 over m to be 1/2. So m equals 2 gives me 1 over m being 1/2. Then, okay, these numbers are different. And it's going to introduce a slight problem. Because keep in mind, my goal, move this down. My goal is actually to show that x is in one of these intervals. And this isn't in terms of two different numbers like 1 over k and 1 over m. It's the same number, like 1/3 and 1 minus a third, or 1/4 and 1 minus a fourth. Whereas here, all I've said is it's like in the interval from 1/10 to 1/2. Those are different, right? So that's a slight problem. The way you can fix that is you can say, well, define n to be the larger of these two. So the max of those two, which definitely exists. So in this case, k was 10, m was 2. So the max would be 10, and I'm saying, okay, pick n equal to that max. And then what we should get is that, okay, so 1 over n, well, n's the larger one, so it's just going to be equal to 1 over k. But 1 minus 1 over m is going to be here at like 9/10. And that gives me the nice symmetric interval I was looking for. Okay, so of course a picture isn't a proof. Prove that. So let's do it. Okay, let's keep in mind, what do I want to get to? I want to show now that, zoom out a little, x is in the closed interval from 1 over n to 1 minus 1 over n. That's my goal. Let's do it. We're going to use these two facts, star and double star. Use those to get there. So maybe I'll scoot that down. What does it mean for n to be the max of these two? Well, if n is the maximum of k and m, it's definitely greater than or equal to both of them. N is greater than or equal to k, and n is greater than or equal to m. Okay. See, that agrees with your intuition. If k was like, well, like over there was 10 and m was 2, then n would be the greater one, 10. And is it true that 10 is greater than or equal to 10? Yeah, it's equal to, but yeah. Is it true that 10 is greater than or equal to 2? Yeah, 10 is greater than 2. So that should be okay. Let's type this down. Okay, but I don't want to talk about n. I want to talk about 1 over n. And so 1 over n, if I'm swapping it, that would be less than or equal to 1 over k. If you take the reciprocal, things flip. The sign flips. And okay, I want to talk about 1 minus 1 over n here. This side. So how can I do that? Well, you would also have 1 over n is less than or equal to 1 over m. So negative 1 over n, thinking about this chunk here, negative 1 over n. Again, okay, the sign would flip. So let me write that better. And if I add 1 to both sides of this inequality, then I get this number here. So 1 minus 1 over n would be greater than or equal to 1. Sorry, I forgot to put a negative sign on this. 1 minus 1 over m. Okay, so hopefully that makes sense. To get from here to here, we took the reciprocal, so the sign, the inequality sign flipped. To get from here to here, I multiplied by negative 1, so it flipped again. to get from here to here, I just added 1 to both sides. That doesn't change anything. So we're left with that inequality. And I still want to show this. How do I get there? Well, let's see here. I'll highlight some things in purple. We know that 1 over n is less than or equal to 1 over k. 1 over k is less than or equal to x. That down. 1 over n less than or equal to 1 over k. And 1 over k is less than x. Similarly, we know that, let's see here, probably have to rearrange some things. Okay, we know that this is true. We know that this is true. Let's rearrange what this looks like. I want 1 minus 1 over m to appear in both places. So let's do, I'll rearrange that 1 minus 1 over m. I'm subtracting the 1 over m, and then adding the x over. That would be greater than. Cool. So convince yourself that argument works. And then what we get when we combine those two is that, okay, x is less than 1 minus 1 over m. And where is it? 1 minus 1 over m is less than or equal to 1 minus 1 over m. Okay, that's a mouthful. But again, we can do our little selection trick and be like, well, that means that this holds. There. Sorry. Okay, less than x. Okay, so that piece holds, which is literally this. So no longer do I want to show it, I actually have shown it. X is strict, or well, not strictly, but x is less than or equal to the right endpoint, greater than or equal to the left endpoint. Okay, so we get the closeness there. It's a lot of work. I don't know if you could maybe get away with showing less work, but let's just remind ourselves where we are now. I wanted to show this, so it started with an arbitrary element of 0, 1, and showed that it was in this, right, one particular set in our union. So, in fact, x, if it's in one of the intervals, it's definitely in the union of the intervals. What we defined as A. So indeed, we started with something in 0, 1, and ended up with something in A, therefore they are subsets of one another. Okay, so that was quite a bit of work. There may be some easier ways to argue it. Again, like the calculus approach is a good start, talking about limits and everything. That at least gets you what the endpoints are. Maybe there are easier ways to argue what whether the endpoint should be open or closed. But this is like the most formal way to do it. So why not show you that way? All right. Well, thank you for watching. Hopefully you can handle at least 2 of the problems on the homework. The third one's going to take a little bit of thinking, but yeah, email me if you guys have questions, and I will see you next week.